If you've seen some of my past videos, when we left off talking about the atom, we left off talking about what was called the planetary model or the Rutherford model. So this comes from Ernest Rutherford, who's the one who discovered the nucleus of the atom, and sorry, my wonky orbits here for my electrons, but he had discovered the proton and he discovered the nucleus through the gold foil experiment. And he kind of conceptualized the atom then as having this mass at the center, this nucleus at the center that was positively charged because of the protons, and there's these electrons that are going around in orbits. And that's his idea of it. This is sometimes called the planetary model. I refer to it as the Rutherford model because the planetary model is also used for the model we're going to talk about today, which is Niels Bohr's model. So I like to try to disambiguate that a little bit and just focus on the people and not necessarily what it looks like, although this obviously is in reference to kind of the solar system here with the Rutherford model being called the planetary model. Rutherford also had predicted the existence of neutrons, even though he himself didn't find them. That was James Chadwick who found the neutrons and then kind of added to the Rutherford model with just this idea that now there's protons and neutrons in the nucleus, and we have these electrons in orbit. Now this idea, this model that they came up with is a physical model. Now models in general in science are just kind of simplified views of reality. And so I like to say kind of simplified, but useful. I mean, there's reasons for them, even if they are a simplified way of understanding things. We can't see atoms. We can barely see atoms with the technology that we have now. Especially in these days, we're talking the early 1900s, the Rutherford model was a way to understand something that was completely unknowable by both our physical capabilities as well as our instrumentation. And again, we're just now getting to the point where we can really get a sense of what atoms look like and be able to understand what that means. So we have to have some way of conceptualizing that, and that's why models are useful. So even though we know that this isn't what an atom looks like, it helps us to have something visual to ground our understandings in so that we can help to describe how things work and what they look like and how they interact with each other. So a physical model then is a model. It's a simplified, useful view of reality, but it's modeling something physical. So let's say physical characteristics of something. Characteristics. And let's just call it a system. So we're looking at physical characteristics of a system. You could have something like a model of a cell in like a biology sort of sense. So you have, a nucleus there, different than this nucleus. Your endoplasmic reticulum, you have your ribosomes, you have all these little things that make up the cell. You can picture those physical characteristics, you can take them out, right? And you can manipulate them, you can play with them. Same idea with your atom here. This was a physical understanding of what the atom is. But Niels Bohr came along in the early 1900s, and he's a Danish chemist. He's actually a physicist. I like to claim all the physicists as chemists is one of the things that you'll notice in all my videos. But I love Niels Bohr, and he's definitely a physicist. But his work on the atom really brings him into the chemistry realm. So he was around in the late 1800s, early 1900s, and his work mostly came about in the really early 1900s, around the same time as Einstein. And he came up with a conceptual model of the atom. And a conceptual model, as opposed to a physical model, is one that models the behavior of a system. So whereas the physical model models physical characteristics, the conceptual model kind of models the concepts, right? This sort of makes sense in terms of the names themselves. So one way we can think about this is something like tide charts. Have you ever seen a tide chart that shows the movement of ocean currents throughout the earth, and you can kind of see those wavy lines that sort of move around, and you can kind of figure out and map where things would go if you dropped it in the ocean at one place, where would it go, kind of depending on these different currents and paths. That's a conceptual model of the ocean. It's not a physical model of the way that the ocean actually looks. It's the way that it moves. It's the way that it behaves. Weather systems would also be in this kind of realm as well. So this idea that the concept, the behavior of something can also be shown in some sort of simplified and useful way. So if we think about this for the Bohr model of the atom, you're gonna laugh because this is my atom, right? It looks like a bullseye. And you can see that I'm terrible at drawing concentric circles. So Niels Bohr is coming around after Rutherford. So we know that there's a nucleus. We know that it's positively charged because of the protons that are in it. We know that it has neutrons in it. James Chadwick came along in the 1930s was when he had discovered the neutron. So neutron came about slightly after the Bohr model of the atom, but you could add to it in the same sort of way. And now instead of having orbits, so if we kind of remind ourselves of the Rutherford model, we have electrons that are kind of in these concentric circles that show orbits around a nucleus. In this way, with the Bohr model of the atom, the electrons are in what are called shells. So let's represent our electrons here with dots. So here's my electrons. The shells that are closer to the nucleus have lower energy. So let's say that that first shell is shell 1, and the second shell is shell 2. The third is shell 3. N here, and we'll get into this in later videos when we talk about quantum numbers. N here is the principal quantum number, and it relates to the energy of this shell. So as we move away from the nucleus here, we increase our potential energy of these shells. So my lowest energy shell is the closest to the nucleus. Further away is higher potential energy. Further away is higher potential energy. We know that potential energy is the energy of position. So if we're thinking about the electrons as having the energies that are in these shells, and the further away positionally those electrons are from the nucleus, the greater their potential is to do some sort of chemistry. And this is how we understand. This is our conceptual model of the atom. Now, if we have an electron in a lower shell, we can get it to move around, energetically speaking, by putting energy in. So if I have a wave here that I put in, so here's some energy, then I can promote or I can excite an electron up to higher energy levels. So it can absorb that energy, that photon, whatever it is that I'm putting in. So I can excite that electron. So this is called excitation or promotion of an electron, where the electron has absorbed that energy and then it goes from shell 2 to shell 3. Now it's important to note, because we're talking quantum mechanics and quantum mechanics is wacky, that the electron absorbs this energy and just is in the next shell. It's not traveling to the next shell, right? I'm not sort of moving through space and time to get there. It was in this shell, it absorbed the energy, now it's in this shell. Okay, so kind of weird. Now once that energy is taken away, or once that electron is no longer excited, it can relax back down. So if we have an excited electron here and the energy is gone, then it can kind of maneuver its way back down to a lower energy shell, which is where it wants to be. When it loses that energy has to go somewhere, right? This is a lower energy. It was at a higher energy. That difference means that some of this energy is going to be lost. So here's my energy out, usually in the form of something visible, potentially. It can also come out in various forms of light. It could come out as an X-ray. It could come out as all sorts of things. Now again, the electron going from the higher energy level to the lower energy level isn't traveling through space. It is going from this outermost ring. It's losing that energy. It's losing that photon. It's emitting that photon. This is called emission or relaxation. So we say that the electron is promoted or is excited to higher levels when it relaxes back down, then it emits a photon. It goes from that higher energy to the lower energy, but doesn't travel in between. It just is. Now the higher energy state here, this excited state, means that we have an atom that's uncomfortable, right? So we have these electrons that exist in higher energy states, and things don't like to be in the higher energy. They want to be the lowest energy possible. So that's called kind of an excited state. So when we have electrons that are in these higher energy levels, this is excited state. And when you have something in the excited state, these higher energy electrons can then go do something, right? So that excited state electron is going to want to go do something because it's got all this energy. It's got something to do, got to go do something. If it doesn't, then it'll relax back down to what is called the ground state. The ground state is the lowest energy configuration. So that's the way that it likes to be, is it likes to be in the lowest energy, it likes to be in the ground state. We can excite it out of the ground state by putting energy in, but then once we remove that energy source, or once that electron kind of moves around a little bit, then it will lose that energy in the form of some sort of photon, and it will relax back down to the ground state. Now, if we're thinking about this for an individual electron, the amount of energy that comes in and the amount of energy that comes out, this is no longer a conserved process. The amount of energy that's coming in is always going to be greater than the amount of energy that we get out. Because these electrons are vibrating, they're moving around. That motion is kinetic energy, so some of this extra potential energy then gets converted into heat, or it gets converted into kinetic energy as these things are vibrating and moving. Again, not moving between energy levels here. The other thing to note about this model is these aren't really where the electrons are, right? I'm not really saying that the electrons are in rings, and these rings are these shells that represent, you know, the energy levels, if that wasn't clear. So it's not that the electrons are sitting here in a physical way, but this is a way that we can understand the movement of electrons. We can understand how electrons move from energy levels, greater energy, lower energy, how they can absorb energy, how they can emit energy. So again, this is a conceptual way that we understand the movement of electrons on an atom. We don't actually think that an atom looks like this, but it's a way to model the behavior of the electrons on an atom. And it all has to do with their position relative to the nucleus, and to this quantum mechanical idea that these shells are in specific fixed energy locations, energetic locations, and I have to have an exact amount of energy to go from one to another. So I can't just overshoot. I can never be in the middle of one of these rings. I'm either in shell 1 or I'm in shell 2, and nowhere in between. So the Bohr model of the atom is useful in understanding the movement and the position of electrons. And from a chemist's perspective, this is important because the outermost electrons, the ones that are in these higher energy shells, are the ones that are doing all the cool chemistry. So these are the ones that we as chemists keep an eye on. And this is a useful, simplified view of reality that we can use to start to predict how elements or how atoms are going to respond in different chemical environments based on the energy of their electrons. Okay, as always, if you have any questions, don't hesitate to reach out. Otherwise, I'll talk to you again soon.